Good afternoon, everyone. I am Vikram, and today we're going to be talking about differential privacy. So, just a few quick things. The aim of this talk is to introduce differential privacy at a basic level, and then we're going to also uh, go into exploring a library in Python called as PyDP, which lets you do differential privacy, like write algorithms using differential privacy in Python. So let's get to the agenda. So we're going to first talk about privacy, what it means. Then we're going to look at a case study in which we look how simple solutions, which we might think are solutions to privatizing the data, might not always work. Then we're going to introduce differential privacy, see how it works, and towards the end, we're going to introduce PyDP, and then we can open up for questions. So just to set some context, like some key terms which keep on coming when we discuss about privacy are, so first is identifiability, which means can I use the data that I'm working with to find out the personal information about any specific individual? Then there's linkability, which means if I have two data sets, can I somehow link the rows of one data set to the rows of some other data set? And then traceability means if I have a data set, can I trace it back to some other database and figure out like history, location, and answer questions like the who, when, what, and why about a particular individual? I wanted to include this graphic, which is when we are browsing the internet, we also unknowingly a lot of people just accept all cookies, for example. So this is one example how your data is being tracked when you're browsing the internet. And if someone gets access to the data, they might be able to identify specific attributes that you have allowed the browser to access. Um, so let's talk about some of the simple solutions. So I'll set some context. So imagine if we have a data set and we want to use that data set for some analysis. And if there's a hospital which has collected a lot of data over the years, and they want to publish this data set for research. So one of the concerns that could be is every individual might not be comfortable sharing the data to everyone who wants to access the data, wants to analyze it. So one simple solution which we might think would work is just redact name and social security. So these two personal attributes we can just remove. And then it would seem that, okay, this is fine, that we could just publish this data and people can analyze it without compromising the privacy of the individuals. But this seemingly simple solution might not always work because there could exist another data set, for example, the voter data set. This could be any public data set, could be free, could be paid, but people can get access to this data set. And if you observe, there are some attributes common between these two data sets. For example, the zip code, the date of birth, the sex of these individuals. And once we identify that there are these common attributes, what an adversary or an analyst could do is that identify unique patterns among these three attributes. So if there's a unique combination of the zip code, the date of birth, the sex of individuals, and if there's some combination of these attributes which are fairly rare in the data set, they can potentially link these two rows, and then we can uniquely identify individuals in the other data set. So out of the control of the medical data set, there was some existing other data set which was able to link rows between these two data sets. And this is a real example in which the governor of Massachusetts, his medical data was leaked to the public because of these three attributes also being present in the voter data set. So now if this seemingly simple solution doesn't work, then how do we make sure that our data remains private and from some other external source we might not be able to identify individuals? So that's the notion of differential privacy, and we'll just set some context, and we'll use this setting in later discussions of this presentation also. So we assume that there are n people in my database, and I have a trusted admin, which is the central store of all the data set, all the data of all these n people. And there's an analyst who can query this trusted database, and have access to the results. And the admin has the responsibility to provide answers to these queries in a way such that the adversary cannot identify individual people, but still be able to get answers to all the queries that they can ask the trusted admin. So here the variable m is called the mechanism, is what the trusted admin should figure out what's the secure m so that the data should not be used maliciously. So so I'll just read out the definition. Differential privacy aims at addressing the paradox of learning nothing about an individual while still learning useful information about a population. So it's kind of paradoxical because you're not learning anything on a singular level, but you're still being able to analyze the data, find out patterns, figure out solutions to problems on a population level. And so if we consider this also has parallels to machine learning, because one of the goals of machine learning is to generalize the data or generalize a function towards a data set, but also not overfit to the data, so that the function should not just blindly learn the rows of the inputs and output rows in my data set. It should be able to generalize to unseen examples. So differential privacy also has a similar goal in which we are still able to do analysis over a lot of the data that we have, but we shouldn't learn something specific about any particular individual. And so in Cynthia Dwork's 2006 work with her colleagues, she mentions that differential privacy is basically a promise made by a data holder, for example, in this case, the trusted admin, to the data subject, to any of the people participating in this data. And the promise goes something like this: you will not be affected adversely or otherwise by allowing your data to be used in any study or analysis, no matter what other studies, data sets, or information sources are available. So it kind of incentivizes people to participate in such studies because they are sure that if they participate or if they do not participate in the study, the analysis would kind of turn out to be the same. So one example which she mentions in her lecture series is the smoking causes cancer example, which means some people might not be willing to give their medical data to insurance companies, for example, because they think that if they are a smoker and the study concludes that, okay, smoking causes cancer, and the insurance company might raise their premiums. But the promise of differential privacy is that even if they contribute their data or they not contribute their data, the study would still result in the same outcome, which is the conclusion that smoking might cause cancer. So this is one example which she used in her work. And so just to put it pictorially, imagine if we have a data set of, say, 100 individuals. We run an algorithm on top of it. We see a certain result. And now imagine if we have another data set, but we just removed one of the individuals in the data set. We ran the same algorithm, and we get another output. If we are able to find out if the outputs of these two algorithms or these two instances of running the algorithm are indistinguishable, that is, I'm not able to figure out any information about the person who was omitted in the study. If this is the case, then that means that the algorithm itself is differentially private. It's able to add noise or do some magic with the output so that I'm not able to figure out what the data was missing or any particular attribute of the person that was omitted from the study. So how is it happening? So what happens is, in any differentially private algorithm, you get a query. You query that to the data set or the database. And then on top of the actual result of the query, you add some noise to it. And since the notion of this noise is very well mathematically formulated, there is a specific technique. There are multiple techniques of adding noise to the answer so that the result of the query is indistinguishable, as we saw in the previous example. So I'll also discuss what kind of noise we need to add, and also on top of all of this, we're also going to see how PyDP enables us to use these mechanisms. Now just putting it mathematically. So this is going to be a mouthful, but I'm going to try to make it easy to understand on what this mathematical definition actually means. So we start with all pairs of data sets D and D prime that differ in a single participant. So something like this. Two data sets, D and D prime, with one participant missing in the other data set. So for all such data sets and a training algorithm M, so M is called epsilon differentially private algorithm. Epsilon is a parameter which we'll also get to in a bit. But M is called epsilon differentially private if for all S in the range of M. So you can consider S as an event that could happen on running the algorithm M over a data set. So the mathematical expression is the probability of an event S happening after running an algorithm M on a data set is almost equal to running the same algorithm on the dataset D prime and the same event happening. So in this case, S could be the conclusion that smoking could cause cancer. So no matter if I run this study on D or D prime, the probability that I conclude that smoking causes cancer is going to be the same, almost same in both the data sets, or in both the data stores like D and D prime, for example. And here, like the almost equal is quantified by the e to the epsilon term that we see here. And epsilon is called the privacy budget. It's something that is an input to the algorithm. So you have to choose an epsilon so that epsilon basically lets you control how much privacy are you willing to give up. So yeah, epsilon is the privacy budget, we call it. So there's no specified range for epsilon, but usually in practice, if we look at algorithms which are epsilon differentially private, the range of epsilon is going to be typically small, so 0.1 to of the order of 4 or 5. So that's the typical epsilon that many of the practitioners use. And the right epsilon, again, depends on how much privacy you're willing to give up. So it needs some trial and error, some sampling, and then we can get to a final value of epsilon. Yeah, so that's the mathematical definition. Now, I'm going to skip this slide for now, but we can come back to this later. So now all of this, we have a baseline understanding of what differential privacy aims to do. And now, so this was during, I recently graduated, and during one of my projects with my professor, I stumbled upon PyDP. So PyDP is a library in Python which lets you do all these differentially private algorithms, right? Lets you write differentially private algorithms. And so they have a small but growing community in which they've added some algorithms already, and they're working on some new algorithms. But it's basically a Python wrapper for Google's differential privacy project. And it was developed by OpenMind. It provides a set of epsilon differentially private algorithms. Uses Python 3. Python 3, you can install it using pip, so all the good stuff. And they have a GitHub page in which they are actively working on some of the issues, like adding support for machine learning algorithms and so on. So I specifically worked on a neural network algorithm, but I used the Google's differential privacy library, which is in C++, but then I was also interested in finding out like what support do we have in Python, and that's how I thought like it might be a good idea to share this out to people about like existence of PyDP. So now let's talk about what PyDP, what are the stuff, what stuff do we get out of the box from PyDP, and what are some of the mechanisms. So I'll talk about mechanisms a bit later, but if you imagine if you want to write any algorithm, it's typically comprised of some set of constructs that you use, reuse, and then mesh together to put out a final algorithm. So you typically use arithmetic operations like, say, in any algorithm, you would use mean, sum, standard deviation, variance, finding out the minimum, maximum, other statistical measures like count and percentile. So all of these algorithms could be meshed together to build a bigger algorithm. And PyDP provides all of these algorithms in differentially private manner. So you can set your epsilon budget. You could also, there's multiple parameters to each of these algorithms which let you customize the behavior. And then there's this notion of mechanisms. So as I mentioned in this slide, the noise that we're going to add, it could be of multiple types. So PyDP provides support for Laplacian noise, exponential noise, and Gaussian noise. So what noises, so all of these are probability distributions, and what PyDP does internally, or according to the definition of differential privacy, what happens is you get your output, or say if you want to compute the mean of a particular data set, you compute the mean, and then on top of it, you sample data points from a Laplacian distribution, you add on to the original answer that you got, and then you get a noisy answer. And this noisy answer is supposed to be differentially private. And so why only these noise and why not random noise? So there's a very good mathematical foundation of it, which I'm not going to go in the detail, but these noises, they're kind of proportional to the sensitivity of your function. And by sensitivity, I mean, I'll jump on one slide, but basically here I have a data set of names and salaries. The sensitivity of the data set is going to be what is the range of the salaries for each individual. So if it in this example, it could be like around 20 or 30K, but if the data set is very large or the values could be very random, the range could be higher. So imagine if the sensitivity of the data set is large, meaning like the output values differ a lot among different rows. So that would naturally mean that I should add more noise to the data set, or more noise to the true answer that I get. And this is what Laplacian noise does. And this is good for like real valued functions, but imagine if I have a query like, what's the most common name in a data set? So I get a string as an answer, say Alice or Bob, and for such cases, Laplacian noise might not make sense because the answer is not numeric. So in this case, we use the exponential distribution and so on. So depending on the type of data, the sensitivity of your data, and what notion of closeness are you using among different data points, we can choose any of the noise mechanisms, and PyDP provides supports for this. So again, pictorially, we have an algorithm to compute a statistic. PyDP would add some noise mechanism, and then we'll get an output. So now this is, so PyDP on their GitHub page, they have a set of Jupyter notebooks which are very intuitive, but I didn't want to go a lot in the detail because the overarching scheme of this talk was going to be just to introduce differential privacy and also introduce PyDP on a very basic level, just to understand what kind of operations are doable and what kind of operations can we do with PyDP. So this is one example in which I'm trying to calculate the mean and average, the mean salary and the sum of all the salaries in a given data set. And if I was gonna do it in a non-differentially private manner, imagine if there's a data set and I could query anything on the data set, even though I don't have access to each individual row of the data set, I could do something like I could ask the database, okay, give me the sum of all the salaries in the data. So it would give out a number. Let's say it is X. And then I would do another query saying, give me the sum of all the salaries of people not named Jeff. So it would sum up these three values and give me a result. Now, given these two values, I could just subtract them and figure out, okay, Jeff's salary is going to be 57K. So that's not differentially private, because even though I'm not asking what's the salary of Jeff, I could still do a series of queries to figure out what's the salary of Jeff. So this is in the non-differentially private manner, but with PyDP, what it does is it first figures out what's the sensitivity of the data, adds noise in proportion to the sensitivity, and then I could do queries like this. So on the third line, I import bounded sum and bounded mean. So these are the two constructs given to me by PyDP. And then I create a query. So this particular part, I set up my parameters epsilon and delta. Delta is another parameter which I didn't touch upon in the definition, but we could consider delta as 0 as well. So epsilon is the privacy budget that I was talking about. And then I create instances of bounded mean and bounded sum. So these two constructs take epsilon and delta, and then I add noise to the data set. And how I do it is I do a quick result. So quick result, every algorithm comes equipped with a quick result method, which does two things. First, the thing first that it does is adds on the data, and then it also computes whatever algorithm that you have chosen. So in this case, bounded mean, for example, and bounded sum, then it computes that result on that particular data. So one concern might be that what if my data set is so large that I'm running out of memory? So what if I have a generator and I want to use like differentially private algorithms on top of this? So PyDP also provides support for incrementally computing the results. So in that case, what you would do is you would incrementally add on the data, and PyDP, what it does internally is it would incrementally keep on calculating the noisy sum and noisy mean. And when you're done with the data, you just have to call a method called result, and then it would give you out the final result. So there's support for that as well. I didn't introduce that example here, but we should know that there's also incremental support for large data sets in PyDP. And then now instead of getting the true sum and true mean, I get noisy sum and noisy mean. And if I expose these APIs, I would be sure that I'm not compromising the privacy of any of the individuals participating. Now, another example is of like for the machine learning practitioners. Personally, when I stumbled upon PyDP, it was due to the naive Bayes algorithm that I was implementing. And so ironically, like the complex example that I'm using is of the naive Bayes algorithm, but this was just an example of support for machine learning algorithms in PyDP. So again, what the aim of this algorithm, of this piece of code, is to figure out what epsilon is the best for their use case, and they're just running the naive Bayes algorithm on a data set. Like I'm imagining that there's a data set which is already preloaded, and so for every epsilon it computes the mean, train and test accuracies, and you get a based on these results you can figure out what epsilon works the best for you. Now just to conclude and open up to questions, some of the things to consider while implementing differentially private algorithms is, actually before that I had skipped one of the slides, which was this slide, and now I want to speak about it. So there are two approaches to differential privacy. One is a local approach and one is a global approach. In practice, both of these are used. For example, the Google's keyboard, which is called the Gboard, what they do is they use local differential privacy. And why they do it is when you type out a partial word, differential Gboard generates suggestions, and those suggestions could be used, technically still could be used to figure out information about, okay, this particular person has typed a particular phrase often. So Google uses local differential privacy, in which they don't trust the Google servers, but what they do is they add on, before storing the data in the servers, they add on noise preemptively and then store the data, and then the adversary can ask questions to the data set and then figure out a solution, and like the data set could give out the solutions. That's the local approach. And then there's the global approach, which we discussed before, which was the data set is the database is trusted. I store the true data, but while giving out the output, I just add on the noise. And in both cases, the untrusted aggregator, they don't have access to the personal information, but it's just the way the data is stored that is different among these two approaches. Some things to consider while implementing differential private algorithms is that Sometimes it's not wise to use differential privacy because if, for example, I want to do it to figure out fraudulent transactions, fraudulent credit card transactions. So in these cases, I actually want to access the true data because I want to figure out what was the amount that was spent, where was it spent, so location, location information, the amount information. So it might not be applicable to every problem that you're working with. So individual level analysis is one such problem. And if the data set is so small that eventually it turns out that differential private algorithm is adding a lot of noise to the data set, so that might also not be a wise thing to do. Then no epsilon is one size fits all, so you have to figure out, play around with your data, play around with a sample of your data and figure out what epsilon works the best for you. Not understanding the sensitivity of your data. As I mentioned, if the data set is too sensitive, one of the attributes is changing a lot, then eventually the noise that you're going to add is also going to be huge, and then you'll suffer from problems with your accuracy. Then choosing the wrong DP algorithm. As I mentioned, if your data set is large, you cannot do something like this by just using a quick result, for example. You have to do it incrementally so that you don't run out of memory. And also failing to properly evaluate the accuracy. So in some cases, accuracy is more important, and you might get away with like losing some privacy. So you have to choose your epsilon in such a way that if you're doing something which is highly, say, a medical research in which accuracy is absolutely necessary, then you have to compromise a bit on your privacy, but you have to choose an epsilon which would let you do so. So yeah, that is all I wanted to share about differential privacy. If you have any questions, I'll be happy to take it. Thank you.
Hello? Oh, sorry. I did have one question. So you said there were some times when you shouldn't use it. You didn't mention performance. Does it typically make things run a lot slower when you're doing data analytics? And is that another reason you might want to shy away from it?
Not really, because in particular for PyDP, if I speak, so all of these attributes, so it's a constant noise. It doesn't depend on your data. It doesn't depend on it. The only thing that it depends upon is the sensitivity. So that's the only computational bit. And typically, sensitivity is fairly easy to compute. So there's no performance, a lot of performance overhead in adding differential privacy.
You can go.
Thank you. So you mentioned a lot about, with sensitive data sets, how picking your epsilon is extremely important. Can you expand on that a little more in terms of, especially in terms of accuracy, at what point you may run into larger issues with accuracy compared to a softer value of epsilon?
Yeah. So if I take the example of Laplacian noise, the noise is typically proportional to the sensitivity of your data and inversely proportional to the epsilon that you use. So in this case, if epsilon is small, it's going to add a huge amount of noise to the outputs. And so what I meant by that was, if in a case you want fairly accurate results, for example, determining any medical outcome, for example, identifying if it's a true positive or false positive for some specific disease. So then choosing a very small epsilon wouldn't make sense because you'll suffer from accuracy issues. So it's like a balance between accuracy and sensitivity. So did I answer your question, or?
Yes, thank you.
Okay, thank you.
Yeah, so I was wondering about how this applies, I guess, to categorical variables, because it seems like it's a little less direct, right? I assume you have to encode them, but then if you do something like target encoding and then apply the noise, is it still, a meaningful variable? And if you do like one-hot encoding, I guess, how do you even apply it, right? Because then if you apply noise to one-hot encoding, right, zeros and ones, it's no longer one hot, I guess.
Yeah, yeah. So the example I talked about was for real valued functions, so the Laplacian noise. But in case our outputs are categorical, what is typically done is you use a utility function, and that utility function gives you a numerical value for each of the category, and then you use something like an exponential distribution. So yeah, I forgot to mention, but Cynthia at work has like a lecture series conducted by Microsoft India, and she goes into much detail on how utility functions are constructed. But basically, similar to sensitivity, there's also a notion of sensitivity with respect to utility functions. So for each of the category, you typically get a numerical value. Then you compute the sensitivity on that utility function, and based on that, you add on the exponential noise. So it depends on what the data set is. So yeah.
Thank you.
Thank you.
Hi, thanks for the talk. I was wondering, I've heard of another technique for privacy, k-anonymity, where you if you're similar enough to k other people in the data set, it's considered to be good enough. I was wondering if there's if you know if there's a relationship between that and the epsilon differential, are those the same thing? Are they different ways to accomplish the same goal?
From my understanding, it's different, and one of the reasons, if I remember correctly, one of the examples that was given in the original paper was about group privacy. So if I want to preserve privacy for a group of individuals, this technique, which of differential privacy, ensures that you still get to control the amount of privacy that you get using the epsilon parameters. So one of the theorems is in this is the composition theorem, in which you could do multiple queries, and if the epsilon budget for each query is say epsilon, then for k queries it would be k epsilon. So you're deterministically knowing how much privacy losses you're suffering. But I think for other techniques this might not be true. But yeah, I might have to check a bit more on that.
Cool, thank you.
Thank you.